Hello and welcome to our daily AP chemistry stream. We are on day 4 of our coronavirus quarantine, COVID-19. Um, Hopefully, I can increase the learning and stuff we talked about yesterday with Gibbs Free Energy. So, as we're waiting for people to join the stream and join in, do we have any general questions or anything just kind of about streaming, about all the stuff that's going on? Hi, Maggie. What general questions do we have? What are you guys? Are you guys enjoying being quarantined? I know some of you have tons of siblings that are driving you crazy. Isaac and Maggie in particular talked about their siblings yesterday as a complaint. Yeah. What other comments? What's going on? How are you guys doing? Hi, Naya. So that's a good question, Lolly. And so those of you that don't know, Lollian's was referred to the stream from one of my honors kids. They're an AP student in, what was it, in Thailand? Yeah. So I'm just familiar with Twitch. I run the esports team for my high school, and so personally I'm a big gamer. I love the game League of Legends. I've been playing games my whole life. So Twitch, I was just familiar with Twitch, and so I decided that it would be a really good free resource to use as we're all being quarantined for COVID-19. So I'm glad you guys are enjoying some extra sleep, Max and Maggie. Yeah, it's amazing when you have open notes on a reading quiz, Micah. How well you can do on it. I'm glad you did good though. I'm glad you did well. Yeah, I can imagine you would be bored. Let's see, Cap Happy. Who is that? I can't remember who that is. I don't know. Oh, it's Zach. Oh, right, Zach Combs. That's who it is. Okay. Maggie has 6 extra. Maggie's auctioning off her siblings. Isabel, hers as well. You guys are ridiculous. Oh, you didn't do them, Micah? Good. You didn't use your notes? Good. Why does it block that? Yeah, but see, Naya, people need to understand that adolescence body chemistry, like, you guys don't even release melatonin until midnight anyway. And so most of you the way your circadian rhythms go is you actually would naturally stay up till midnight and sleep in till somewhere around 8 a.m. And so having us make school start at 7 is kind of cruel. So, but yeah, no, you shouldn't stay up on technology past midnight. But technically, your bodies don't actually go to sleep until midnight-ish. So yeah. You do. So if you want to not screw up your sleep cycle, you kind of want David, I will tell you how to live your life. You technically should like stop using electronics and stuff around 10, so that your body has a chance to kind of wind down and you can get to sleep by midnight. But it's kind of how your natural body rhythms usually go when you're an adolescent. Yeah, that happens, Isabel. The way, like, our way of getting tired and awake is weird cycles. Um, but yeah. The problem is, high school students have so many, like, after school activities, whether that's jobs or the homework or sports or whatever, that they push the earlier so that everyone can get to those things. In a perfect ideal world, we would start high school at 9 a.m. and go till 5. Having high school around 9 to 5 would be best for everybody involved, but that's okay. Because you have my kids that are 4 and they wake up at 6:30 just automatically. That's just what they do. No, we couldn't do 9 to 3:30, Isaac. That's not long enough. You couldn't get enough class time in. We have more stuff we have to learn. Maybe 9 to 4 if we cut out some of the less important classes, but I didn't say that. Yeah, Joel. No, I think that's kind of stuff is fascinating. I think psychology is really interesting. Um, but that's just kind of a side note. Oh, there's a notification here. Someone. Oh, Tiara. Okay, sorry. Um, okay, no, history is important, Michael. We've talked about how history is important. All right, okay, let's focus in on chemistry. It looks like we've got most people in. Let's talk about kind of what we talked about yesterday. So as a reminder, yesterday we were focusing on Gibbs free energy, and we were talking about how we can use the change in enthalpy, the change in entropy, to calculate this change in Gibbs free energy, and that allows us to predict whether or not a reaction will be spontaneous. Okay, and we talked about how we can use the heats of formation and we can use the entropy values to take, we write them for an equation, we take the products minus the reactants multiplied by their coefficients to give us our delta H of the reaction and delta S of the reaction, right? We got all these delta H and S values from the charts on page 203, page 411, or page 601. Or Isaac posted the thermodynamic data in the Discord chat, so you can look and pull that up. You might have to scroll up a little bit. A lot of people were asking questions yesterday afternoon. Maybe I should pin that message. You know what? I'm going to do that right now. I'm going to pin that so you guys can use that. There we go. Okay, so that message is pinned to the AP questions stuff, so you can look at it. Yeah, Mikey, I can't take donations yet. Although at the end of the week, I will probably, sometime next week, I will probably become a Twitch affiliate just because that's how it works. And so, yeah. Anyway. All right, so we got the delta H of the reaction, we have the delta S of the reaction. Using those two values, we can then calculate delta G equals delta H minus T delta S. And so if we're at 25 degrees C, then we have 298 Kelvin. We plug in the delta H value, we plug in the temperature, right? We plug in the delta S, remembering that our S value needs to make sure that it's in kilojoules per mole. The chart, one of the charts is in joules, one of the charts is in kilojoules. So you might have to do a conversion for that. I'll work on getting emotes, and I don't know if I'll mod you, Isabel, but I might get a mod or two if chat gets a little crazy. But usually I can mod the chat well enough right now. So we plug in these values and we get the delta G is a positive 56.6 kilojoules per mole, which means that it's non-spontaneous. Okay, so again, that was just a quick recap of what we did. We talked about how entropy is a measure of randomness or disorder, and how your molecules can be in different states. There's different microstates is what we called it. The more way that a molecule can move around, we talked about how gases have very high entropies. Solids and liquids have much lower entropy values. The more floppy a molecule is, the more entropy it has, right? Little small molecules have very low entropy. So something like diamond has pretty much the lowest entropy because it's a solid, perfectly ordered crystal. When it says calculate delta S, you can. Isaac, you can either do it in kilojoules per Kelvin mole or you can do it in joules per Kelvin mole. It's just a quick shift back and forth. Good morning, DJ. So yeah, in 1819, I think on the answer key, I don't remember what I have it in either joules or kilojoules, but you move the decimal 3 places, it's the same. Okay. All right, so Roman numeral 2, let's dive into it. Let's talk more about delta G. Now, you'll notice I am going to add this little symbol here. I kind of ignored this yesterday because I didn't want to confuse you guys. I didn't want to talk about it. Today, I'm going to talk about what this not symbol means. So this is delta G naught. If the book have it in kilojoules or in joules per Kelvin mole, you can do it in joules per Kelvin mole. So yeah, so this is not as in NaU. So let me. That's a not symbol. The not is important, and we're going to talk about why that is kind of right now. That's where we're going to go with this, is what is the significance of the not and what does that mean. Okay, so that's actually letter A. Right. So what does not mean? Right. What does this little symbol mean? Yeah, you can hear my my daughter crying in the background. What does this not mean? Right. What is this little degree? It's not a degree symbol, but it kind of looks like a degree symbol. Yeah, poor Claire. I think she's probably upset about something. She's 2. She's upset about stuff all the time. That's just how 2-year-olds work. All right. So let's talk. What does that not mean? What does that not mean? The not means standard conditions. Right? In particular, it means gases are at 1 atmosphere of pressure and solutions are 1 molarity. Okay. So standard conditions our gases are at 1 atmosphere of pressure and our solutions are at 1 molar. Okay. Okay. No, temperature. Yeah. So when we say when we talk about the not symbol doesn't imply temperature. You can say that standard conditions are 25 degrees Celsius, but when we say not, that doesn't mean temperature. So it's a little bit of a weird, like, does it mean 25? Does it not mean 25? In this case, when you have the not, right, when we're talking about the standard conditions that make up, delta G naught, we're just assuming the gases are at 1 atmosphere and solutions are at 1 molar. If a problem ever says standard temperature for solution or for delta G calculations, standard temperature is 25 degrees Celsius. So sometimes that gets wrapped into standard conditions, sometimes it doesn't. Okay. So when we look at this equation, right, technically the equation should be delta G naught equals delta H naught minus T delta S naught, right? All of the values that are in the tables are these standard conditions. They're all calculated based on gases being 1 atmosphere of pressure and solutions being 1 molar. Okay, so make sure that the technical thing to write down is that delta G naught equals delta H naught minus T delta S naught. Yeah. Okay. Let me see. Let me look at my notes real quick. Make sure I know what I'm doing next. Okay, cool. So we talked about this a little bit yesterday, but I just kind of wanted to reemphasize and reiterate. Let's see. On the table above is some alpha seminex compound. I don't actually know. I'd have to look at that, Isaac. Yeah. So Logan, we are going to get into that probably today. More likely tomorrow, about problems not in standard conditions. We'll talk about the convert. There's an equation that can convert between delta G naught and the just plain old delta G, and we'll talk about that tomorrow. I don't think we'll get to it today, so look forward to that tomorrow, Logan. All right, so let's do a little bit more about kind of what this all means. So I'm going to flip the page. Does everybody have all this down before I flip the page? Again, if you're just trying to focus on the notes and you're not actually writing it down, that's totally fine. You just might want to go back to the VODs on YouTube later and kind of get everything down. Yeah, so technically, Naya, the stuff we did yesterday, this equation up here, if I was being technical, I should have included the not symbols here. Sometimes I'm just lazy and I just don't write it. Joel, the homework's going to be due next week, probably Tuesday. Let's say Tuesday. but it's a lot. So you need to start doing it if you haven't started doing it yet. Okay, so delta G equals delta H naught, or delta G naught equals delta H naught minus C delta S naught. Let's talk a little bit more about this. So yesterday, actually, hold on, I'm confusing myself. Letter B. How will we turn it in? That's a great question, Micah. I probably will just post the key, have you guys grade it, and then just record your score. It'll be kind of an on your honor thing. I trust you guys. Letter B. The values of delta G naught. Okay. I'm glad TJ's watching. He can have a little review. Okay. Good job, Isabel. Keep it up. All right. So values of delta G naught. Okay. So if delta G naught is greater than 0, meaning it's positive, right? Greater than 0, positive. What does that actually mean? If delta G naught is a positive value. Ooh, careful, Isaac. If delta G naught is positive, it is non-spontaneous. Right? We want delta G naught to be negative, which is number 2. Now, something else I want to point out about these values, no, you're good, Isaac. Something else I want to point out about these is if we have a general reaction, let's just imagine we have a reaction A in equilibrium with B, okay? So there's, Naya, the way Twitch works is there's a little bit of a lag. So when you type a question into Twitch, the chat, it'll pop up on on the actual screen about 5 seconds later. So you just have to kind of get used to when you ask a question, it won't appear for another 5 seconds. Just kind of how the nature of it and how it works. Because it's got to process the video, render it, send it back out to the internet, all those wonderful things. So yeah, just used to a couple seconds for the chat to come onto the stream. All right, so let's talk about if we have A in equilibrium with B. So if we have A in equilibrium with B, and let's say we calculated the value of delta G naught, okay? So, oh no, Isaac, we're not done with equilibrium. Don't. We're never done with equilibrium. Okay, so if A is in equilibrium with B, hi TJ. If A is in equilibrium with B, and if we calculate delta G for this reaction, and it turns out to be negative, right? What that means is that A is going to turn into B. Okay. If we calculate delta G and we find that delta G is positive, right? That means that the way this reaction is written, it's going to be non-spontaneous. But if this is positive and it's non-spontaneous, what that actually means, instead of this reaction taking A and turning it into B, it would take B and turn it into A. So let me see if I can emphasize this. So if this is 1 molar and this is 1 molar, right, these are aqueous. Okay. If delta G naught is less than 0, then A goes to B. If delta G naught is greater than 0, then B goes to A. Right? So another way, when we say something is spontaneous, it means that the forward reaction is going to occur. When we say something is non-spontaneous, we can think of it as being that the reverse reaction is going to occur. So if delta G is less than 0, it means my reaction is spontaneous, and A will turn into B. If delta G naught is greater than 0, my reaction is non-spontaneous, and therefore B is going to turn back into A. Now, this last one. What if delta G naught equals 0. Yeah, Sarah. So you just change the sign, right? So if you reverse a reaction, just like with our delta H, you know how delta H turns from negative to positive when you flip a reaction around. If you reverse an equation, then the delta G naught, the sign also changes from negative to positive and positive to negative. So it's not necessarily, Micah, it's not necessarily that A equals B, but it means that we're at equilibrium. It means that neither the forward nor the reverse reaction is going to happen. So it means that we're just going to sit. So in this case, yeah, technically, since they're 1 molar, they would be equal to each other. But the idea is that if delta G naught equals 0, it means we are at equilibrium. We have A turning into B at the same rate that B turns back into A. And so if delta G is less than 0, the forward reaction will occur. If delta G is greater than 0, the reverse reaction will occur. If delta G naught equals 0, then we are at equilibrium. Yeah, DJ, that's actually a really good connection. Delta G is like comparing Q to K. When delta G is less than 0, that means that Q is less than K. When delta G is greater than 0, that means Q is greater than K. And if delta G equals 0, it means Q equals K. And we'll talk more about that a little bit later. No, K doesn't equal 0. In this case, K would, if these were 1 molars and if delta G equal to 0, then K would be 1 because it's products divided by reactants, coefficients turned into exponents. Yeah. Okay, cool. Let's go back to our, let's think about our equation again. So if delta G naught equals delta H naught minus T delta S naught, right? So what combinations of delta H and delta S are going to give us? Okay, so let's think. We've got 4 possible combinations, right? So delta H can be positive, delta S can be positive, delta H can be positive, delta S can be negative. Delta H can be negative, delta S can be positive, and delta H can be negative, and delta S can be negative. Okay, so we can have these 4 combinations: positive, 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 negative, negative, positive, and negative, and negative. Okay, as a reminder, what that means is, right, if delta H is positive, that means we have an endothermic reaction. If delta H is negative, that means we have an exothermic reaction. If delta S is positive, that means our reaction is becoming more disordered, right? It's gaining entropy. The entropy is increasing, more disorder, more randomness. If our delta S is negative, that means it's becoming more ordered, right? Less disordered. The entropy value is decreasing. Okay, so we have all these combinations. We have an endothermic with more entropy. We have an endothermic with more order. We have a exothermic with more disorder, and then we have an exothermic that's becoming more ordered. I'll keep going through this, Mike. I'll keep repeating it. So what I want to do is I want to say, what does this mean in terms of delta G, right? What can we predict if these are the signs? What does that mean about the signs for delta G, right? For example, let's see. Is there a combination of these signs that will make delta G always be positive, right? Is there a combination that would result in delta G always being positive? Which combination of delta H and delta S would result in delta G always being positive? Yeah, Zach Coombs, good. Positive, negative, right? You got to be careful. There's a negative in the equation, right? So we want delta H to be positive and delta S to be negative. So if delta H is positive and delta S is negative, delta G is going to be always positive, aka non-spontaneous. Right? So, good. A lot of you guys are saying that in the chat, right? So because of this minus sign in the equation, a positive delta H and a negative delta S would result in a positive delta G. Now, you got to remember temperature is not going to affect the sign because temperature has to be in Kelvin. And so the temperature will always be a positive value because it has to be in Kelvin. So the idea that positive and negative is going to be always positive, always non-spontaneous. Okay, what combination is going to be always negative or always non-spontaneous? Yeah, it's going to be the opposite. It's going to be the negative positive. So this combination will give us always negative, right? Meaning it'll always be spontaneous. Okay, so what does that mean? That means that an endothermic reaction that becomes more ordered will always be non-spontaneous. You cannot have an endothermic reaction, a reaction that takes in energy, and a reaction that becomes more ordered occur by itself. You have to manipulate it with some outside forces. You have to do some other stuff, okay? But an endothermic reaction that becomes more ordered will never be spontaneous by itself. Now, an exothermic reaction that becomes more disordered will always be spontaneous. That's why combustion reactions are so violent, right? They are a exothermic reaction. They release heat, and they are becoming more and more disordered because they're making carbon dioxide and water vapor, and so they're producing all these gases, okay? So the idea that an exothermic, more disordered reaction will always be spontaneous. Now, the other two sign combinations are interesting, okay? If delta H was positive and delta S was positive, the other factor we have is temperature, right? So what kind of temperatures would result in a positive, giving me a spontaneous delta G? What temp do we want, a high temperature or do we want a low temperature to make it so positive delta H, positive delta S results in a negative delta G? Yeah, Naya, good job, guys. High temperature, right? So the reason why it's high temperature is because of this negative sign. As we increase and increase temperature, this quantity gets more and more and more negative, which means that it can overcome the positive delta H. So what we would say here is we would say that this is spontaneous at high temperatures. Right? And so consequently, it would be non-spontaneous at low temperatures, right? Non-spontaneous at low temperatures. So these are things like if we think about ice melting. So for example, if you take ice and you try to melt it, that is an endothermic reaction, right? That pulls in heat, but it also is becoming more disordered because a liquid is more disordered than a solid. And so we know that at very low temperatures, ice doesn't melt. And at very high temperatures, ice does melt, okay? And so something melting, or even something turning into a gas, something boiling, is going to be described by this positive-positive interaction, okay? Where it's spontaneous at high temperatures and it's non-spontaneous at low temperatures. Okay, now what if we look at this negative-negative combination? What is that negative-negative combination going to give us in terms of temperatures? Yep, good, Maggie. Right, so this is going to be spontaneous at low temperatures. Right, so this exothermic reaction that becomes more ordered is going to be spontaneous at low temperatures, okay? Because if delta H is negative and delta S is negative, that negative times that makes this a positive term overall. And so if temperature were to get greater, eventually that would overcome my delta H and it would make it so the overall was positive. But at low temperatures, when this term is small, then it could be there. Yeah, so Haley, when we say spontaneous, we mean spontaneous under certain conditions. Okay, so these combinations will always be spontaneous. If this combination is always spontaneous, this combination is always non-spontaneous, regardless of the temperature, right? But these ones are spontaneous depending on the temperature. And so if your temperature results in a negative delta G, it is spontaneous. But if your temperature is too low, or too high, depending on the context, we would consider it to be non-spontaneous. So if it currently is at a temperature that's non-spontaneous, we would call it non-spontaneous. But if you could raise the temperature to make it spontaneous, then it would make it so at that temperature it would be spontaneous, but under the current situations, it's non-spontaneous, right? So when you decide whether a reaction is spontaneous or non-spontaneous, you have to consider the signs of delta H and delta S, and then also potentially the current temperature that you are at. Hopefully that helps, Anna. Okay, cool. I'm going to move on to the next page. Everybody got all this? Okay, let me double check my notes real fast. Oh, I know what I want to do. Okay. Yeah, this is the last thing I want to do. Cool. So what I wanted to do is I wanted to refer back to that problem that we did earlier. So number 4, right? I wanted to refer back to the problem we did yesterday. So if you remember yesterday, seriously, TJ, yeah, it's been 2 years since you've had it, right? So if we go back to what we did yesterday, we found that delta H was 98.8. Right, 98.8 kilojoules per mole. And this is technically delta H naught. And we found delta S naught to be 0.1415 kilojoules per mole Kelvin. Okay, so again, not technically delta H naught. So if we go back to the problem from yesterday, right, we found these values, okay, our 98.8 and our 0.1415. And we said that it was at 25 degrees C. And we said at 25 degrees C, per mole Kelvin. At 25 degrees C, delta G is positive 56.6 kilojoules per mole, and we said it was spontaneous. But let's think about this combination. So we have a positive delta H and a positive delta S. If we have a positive delta H and a positive delta S, looking back, when does that become spontaneous? Does it ever become spontaneous? Yeah, high temperatures, right? Positive delta H, positive delta S is going to be spontaneous at high temperatures. And so what we're going to do with what the question I'm going to ask, right? The question I'm going to ask is when or at what temperature would the reaction change from being non-spontaneous to spontaneous? I could fit it. Sorry, that's terrible handwriting. Okay, so at what temperature would the reaction change from being non-spontaneous to spontaneous? Ah, Naya, you got it. Ding, ding, ding. Extra points to Naya, right? We're solving for when delta G equals 0. Okay, so we're solving for the temperature when delta G equals 0, right? Because currently at 25 degrees C, delta G would start out at 25 degrees C, delta G is going to be a positive value. And so as we increase the temperature, that positive becomes smaller, until at some point it's going to switch to being negative. That switching point is when G equals 0. So we're going to take our delta G naught equals delta H naught minus T delta S naught. We're going to plug in 0 for delta G naught, right? So if we plug in 0 here, okay, and we plug in 98.8 kilojoules per mole minus T, we're solving for the temperature, times 0.1415 kilojoules per mole Kelvin. Okay. How would we rearrange this equation to solve for temperature? Right. So algebra might be a little tricky. We basically take this whole term and we add it to the other side, and then we divide by the delta S. Max, that's a great question. Sometimes we plug in, sometimes you can just say non-spont or spont. Okay, so recap, Joel. Why are we trying to find when G equals 0? Let me show you with the numbers why that works in a second. So yeah, so you could also subtract delta H and divide by negative delta S, or in my opinion, we can just add this term to the other side. So T times 0.1415 kilojoules per mole Kelvin equals 98.8 kilojoules per mole. Divide both sides by the 0.1415. Okay, so then our temperature equals, right, kilojoules cancel, moles cancel. We have per Kelvin, which turns back into Kelvin, and a lot of people are saying 698 Kelvin. Right, and if we wanted that in Celsius, that would be what, 425. Right, which isn't that hot. You can do that in your oven. Right. Sorry, I angled here. Okay, so again, why are we solving for delta G equals 0? Joel asked a really good question a while ago. So let's recap. Okay, the question asks, at what temperature would the reaction change from being non-spontaneous to being spontaneous? So when we solved this problem yesterday, we plugged in 25 degrees C for the temperature, or 298 Kelvin. When we plugged in 298 Kelvin for the temperature, we found that delta G was a positive value, right? Okay, because we took 98.8, we minused 298 times 0.1415. I think we ended up getting like 50. Okay, as the temperature goes up, right, as our temperature gets higher and higher and higher, in this reaction's case, this term gets bigger and bigger and bigger. And so if we're subtracting a term that's getting bigger and bigger and bigger, this delta G is getting closer and closer and closer to being negative, right? And so at some point, the temperature gets hot enough that we're going to swap from delta G being positive to delta G being negative. And the point when a number changes from being positive to being negative is 0. So remember, when delta G equals 0, it doesn't mean it's spontaneous. That's just when it changes from being non-spontaneous to spontaneous. Technically, this is the temperature that we're at equilibrium. If we were to raise this temperature a tiny bit higher, if we were to go to like 698.1, all of a sudden the reaction becomes spontaneous. Okay, so delta G not equaling 0 is our tipping point. It's the equilibrium. It's where we change from non-spontaneous to spontaneous depending on how we change the temperature. Okay. I think that's as far as I wanted to get today. So we still have some extra time left. Those of you that have started the homework, are there any maybe general questions that we could ask? If you have specific questions, right, hop into the Discord at noon. I'll be able to answer questions from noon to 2. A lot of people were doing that yesterday. They had kind of dived. They'd gotten into the homework and do that. So again, if you haven't already checked it, reminder on Canvas, okay, that the chapter 16 assignment sheet is here, okay? No, yes, TJ, it's okay if you don't do the homework, okay? Mikey, if you sound good, you're good to go. Isabel, how far can you get to now? You can get all the way up to, I think, problem 53. Oh my gosh. Okay. So yeah, you can go all the way up to 53. So you can do 5 all the way to 53. So you can get, really far. Okay. So again, people that are asking the questions of how far you can get to 53. Right, so you should be able to do all of these problems. Okay. Yesterday, a lot of you, if you're working well, you got up to 19. You can go all the way up to 53 now. Yeah, Lauren, it's a big yes. Don't feel like you have to do that all tonight. Okay, but know that you can go that far. If you haven't started yet, make sure you start this afternoon. The first couple problems go really quick, Naya. I think, I don't know, you'd have to ask Isaac or somebody how much they were able to do. Maybe a half hour to an hour. TJ, don't make me ban you. Bryce, I don't think the lack of labs will affect us too bad. If it comes down to it, there are some videos I can give out that show people doing labs and kind of demonstrate some things like that. And so we'll worry about that when we get there. But thankfully, up to this point, we were able to do most of what I would call the essential labs for understanding AP. There's just a couple other things. Yeah, I guess you're right, DJ. Okay, so it looks like it took Isaac about an hour to do up to 19. Oh, David, why you gotta ask the hard questions? So what did the units represent of kilojoules per mole? I'm gonna hold off on that. Give me a chance to kind of form a better opinion, David. That is a fantastic questions. Yeah. Let me get back to that tomorrow. Remind me again tomorrow on that, and I'll come up with a better answer for that tomorrow. There are experimental design questions on the AP Chem test, Naya. It's usually only like 1 or 2 in the free response, and so we'll get into that. Any other recommended websites? Not currently. I mean, if a topic comes up and you guys want to know more about it, I can recommend a specific topic then. But your study books are going to be really a really good resource, which you can worry about as we get there. I think they're just pictures of leaves and trees. It's just my wife being artistic. No, I didn't ban that random chem professor. He just hasn't been back. I guess he's not been using. So we use so our textbook is Masterton and Hurley. It's kind of the author of our text. Right. I really like this book. I think it's a fantastic just chem book. For like AP review material, I told them to just get either the 5 Steps to a 5 or the Princeton Review are both really good review books you can buy on Amazon. I don't know what my kids are doing. I think they're downstairs, but here, we'll adjust this. No, my kids aren't gamers. My son is 4. He does like video games, though. I think he probably wants to get into it. When I'm playing, he always kind of wants to jump in and play as well. So, okay. Any other last questions? We're going to end a little early, which I'm sure everyone's going to be fine with. Reminder that at noon, I'll be in the Discord, and so you can jump in there. You can go all the way up to 53 for the homework. Okay. No, the esports tournaments are still going. We actually had our match. We beat a team this past week. We're playing Provo next week because the nice thing is you can play from home. So all our esports teams are still going. So finals for what, Max? Yes, that's why there's a semicolon at 53 and not a comma, because that's the way the lecture gets broken up. Oh, final questions. Yeah, that says final questions, right? Brighton has a League of Legends esports team. So we're competing through a company called Play Versus. Yeah, I'll actually probably start streaming our matches. I streamed our practice last Monday. So I'll maybe stream them on the channel too. So if you guys are interested in learning more about esports, you can jump into that. Yeah, I know, Mikey. All the sports are getting canceled. It's kind of a bummer for all the seniors that are playing sports. And like, if, yeah. Joel, the problem with Rainbow Six is it's a mature game. And so when you get to those rated M games, people get a little squeamish about them. Yeah, Isaac, if you want to post it, go ahead. Um, Isabel, I'm not sure about the quarantine. They said they were going to reevaluate after the end of 2 weeks. And so, yeah. So we do have so the company we use does sponsor Rocket League. I just don't know if we have enough interest in playing Rocket League. I'd have to kind of look out. Yeah, and again, Mikey, the problem with CS:GO is CS:GO is also mature rated. I personally think the quarantine is at least going to go through spring break. I think we're going to hit 4 weeks with it. So this is going to be the new norm. So I don't want to keep you guys too long. I want to keep the stream a little short so we can people can post it. Let's go ahead and kind of just end here. Yeah, Smash is gone. We had a thing and that's gone. Our current stuff doesn't use it. We might bring it back next year. We're just going to kind of see. Okay, if there's no other kind of important Twitch channel or Twitch chats, homework chat, we are going to, yeah, it could be 8 weeks, it could be 4 weeks, it could be, who knows. Okay. You guys have a great rest of the day. Again, if you're working through the homework, you have questions, I will be in the Discord from noon to 2. Okay. Hey, no problem, Lolian. Good to meet you, man. You guys have a great rest of the day. See ya.